All right, we're going to talk today about the chain rule, which is when you have the derivative of a composite function. So we know what to do when we take the derivative of the addition of functions, the subtraction of functions, the multiplication of functions, and the division of functions. The last operation we have then is the composition of functions, where one function is inside of another. So if I am going to take the derivative with respect to x, of f of g of h of k of x, I'm going to start by taking the derivative of this. So that one gets darker. And then I'm going to leave g, h, k, and x all alone. So g, h, k, and x all alone. Then I'm going to multiply taking the derivative of the next layer. Okay? Then leave h, k, and x alone. Then I'm going to take the derivative of h, the next layer, leave k and x alone. Finally, I'm going to take the derivative of k, leave x alone. You could consider that you're taking the derivative of x, but what's the derivative of x? It's 1, so you can multiply by the 1 at the end. So what's happening is every time you take a derivative, you are peeling back a layer, and you know you're done once there are no more layers. Just like onions. All right, so if f and g are both differentiable, which remember differentiable is we are able to take the derivative, and capital F is what we're going to call the composite of f and g, then capital F is differentiable. Two differentiable functions composed together will also be differentiable. And capital F prime is given by the product. So capital F prime is equal to the derivative of the outside, leave the inside alone, times the derivative of the inside. So again, we're considering this to be our outside function, and this to be our inside function. So I'm going to peel away little f by taking the derivative, leave that next inside layer alone, times the derivative of that inside layer. So I take the derivative of f, I take the derivative of g, there's no more functions to take the derivative of, I am done. So f prime of x then, this is what our M&M friend is about. If you bought M&Ms, go ahead and take one M&M and put it in your mouth, but don't bite it. Okay, we're going to just be removing layer by layer. So what's the first layer that you remove? The candy shell. And we're going to leave the chocolate and the pretzel, switching all my colors around here. We're going to leave those alone. Then the next layer that you come across is that chocolate. We're going to peel that away. And we have the pretzel still on the inside. And then the derivative of the pretzel, you have completed eating one M&M. Okay, so that's the way to think about that. Another way to think about this is derivative of the outside. Leave the inside alone. Multiplied by the derivative of the inside. Okay, so again, this is when you have a function inside of another function. In Leibniz notation, so where we're taking those derivatives with respect to x, if y equals f of u, yes, haha, and u equals g of x, then what ends up happening, if we think of f of u, that's really f of g of x, right? So we've got a composite function going on. Well, then the derivative of y with respect to x is going to be the derivative of y with respect to u times the derivative of the inside which would be the derivative of u with respect to x, well, look what happens. du's cancel out, and that's our dy dx. Okay, so there's going to be some problems in your textbook that ask you to identify what is the inner function and what is the outer function. So in this case, g of x is our inner function, and f of x would be our outer function. Your packet has a typo. It says sine. We're not going to take sine. We're just going to take the sine of x squared, and we're going to work to find the derivative. So when I think about the sine of x squared minus 4, I see a polynomial function, and I see the sine function. So to take the derivative, f prime, I don't necessarily love that notation. We'll just call this, I'll write it all out. F prime of g of x times g prime of x. I'm going to take the derivative of sine, which is cosine, and I'm going to leave the inside alone. I'm going to go back up here to my original equation. The next layer that's there is x squared minus 4. So I'm going to multiply by the derivative of x squared minus 4, which is 2x. So my final answer is the cosine of x squared minus 4 times 2x. It's the derivative of the outside, leave the inside alone, times the derivative of the inside. Now there's nothing left on my original function, so I know that I can stop. All right, the derivative with respect to x of secant of 3x. So again, I'm going to identify I have the secant function and I have the 3x function. Well, the chain rule would say take the derivative of the outer function. So the outer function here is secant. Because if you think about subbing in a number for x, you would first multiply it by 3, then take the secant. So we want to undo that. We want to take the derivative of secant, then take the derivative of 3x. So I'm going to take the derivative of secant is secant times tangent, leaving the argument alone, the part on the inside, times, from the chain rule, the derivative of the inner function, well, the derivative of 3x is 3. Okay? So again, you want to figure out what is your outermost layer, take that derivative, leave the inside alone, times the derivative of the inside. Okay, so this one's a lot like the one on the first slide. We're going to take the derivative with respect to x of f of g of h of k of x. So I'm going to start from the outside, because if I picked a number for x, I would run it through k, then through h, then through g, then through f. So I want to undo that. I'm going to take the derivative of f, and I'm going to leave the inside alone, g of h of k of x. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. So now f is gone. So now I'm going to take the next layer. I'm going to take the derivative of g, and I'm going to leave h of k of x alone. That one's gone. Now I'm going to take the derivative of h, so h prime, and I'm going to leave k of x alone. Finally, I'm going to take the derivative of k prime, leave the x alone, and then if I wanted to, I still have this x right here, so I could say the derivative of x is 1. Now I've used up all of my functions, right? So I know that my derivative is over. This isn't just a chain after chain after chain after chain. All right, here, when I go to take the derivative, I see two different functions. I see x squared minus 3 is a function that is being raised to the 50th power. Well, if I want to take the derivative with respect to x, if I were to plug in a number for x, I would square it and subtract 3, then I would raise it to the 50th. So to take the derivative, I want to undo the 50th power first. And the way I do that is by swinging down the power and dropping the exponent by 1, all while leaving the inside alone. So I just took care of the function in red. Now I'm going to multiply by the derivative of the inside. Well, the derivative of x squared minus 3 is 2x. And that's my final answer. Okay? 4 examples for you to do on your own, / with your group, / with your guardians. So I'm going to ask that you look real quick at your notes and recognize that it shouldn't say tan, tan, and it shouldn't say sine, sine, cosine, cosine. Okay? That was just typos for when we transferred to Google Docs. What I am going to have you do is we have 4 problems. Oh, I guess I only have 2 on this slide. 2 on this slide, 2 on the next slide. I'm going to have you pause your video and try all 4 problems. And then come back and check your answers with mine, and I'll explain them. So go ahead and pause your video, and then come back and listen to my explanations. Pause it for yourself, try it on your own, and then we'll confirm. Okay, so here's my first 2. I chose tangent to be the outside function, right? Because if I plugged in a number for x, I would do the blue stuff, then the red, which means to take the derivative. I want to undo the red, then the blue. So the derivative of tangent is secant squared. The derivative of 2x to the third minus 1 is 6x. And I'm done. This is just me cleaning up the answer for how it might appear in a textbook. This one I've got 3 functions, sine, cosine, 3x squared plus 5. Well, if I were going to actually evaluate this, I would do the purple, then the blue, then the red. So to undo it, for the derivative, I need to take the derivative of sine, which is cosine, leave the inside alone, times the derivative of cosine, which is negative sine, leaving the inside alone, times the derivative of 3x squared plus 5, which is 6x. And then again, this is just me cleaning it up. Make sure you multiply by the negative sign. Don't just write minus sign, because otherwise it looks like subtraction, and we don't want that. Okay, yikes. There's a lot of math on this slide. Let's talk about this first one. So what you want to notice is that overall, this is going to require a product rule. And the product rule is first times the derivative of the second plus the second times the derivative of the first. The only thing that gets more interesting here than the ones we've been doing is that when you go to take the derivative of the second, or the derivative of the first, their derivative just happens to need a chain rule because they are a function in a function. So I tried to color code things the best that I could. The one that I boxed in with the 3 yellow check marks, that is an okay final answer. That is following the product rule, done, over, etc. The line below it is just cleaning things up, like 3 times 10 is 30. 4 times 12x is 48x, okay? This line down here is some crazy fun factoring, okay, taking out GCFs. So a 6 can come out of 30 and 48. 4x to the third minus 7 to the third can come out of that one and that one. And let me get my pink pen here. A 3x plus 2 can come out of each of these, right? So if I take out 3 of these, I'm going to be left with 1 of them, which is what we see right here from 4. If I take out 9 of these, gone. 48 divided by 6 leaves me with 8x, so that's that part right there. 4x to the third minus 7 to the third, I yanked it out. 3x plus 2 to the 10th, I took out 9 of them, so I'm left with 1 of them. Okay? Don't have to worry super much about that algebra, but good to remind yourselves about how to find a GCF, even when you have these binomials that are technically factors that you can take out. This last one, I rewrote this as 4x to the third minus 5 all to the, oops, that should be a negative 1/2, which makes this a negative 3/2, which makes this to the third. Sorry about that. Caught myself. Rewriting it as the square root, but up in the numerator so that I can use my chain rule. So the 4 just chills, right? That's a constant multiple. 4's just hang out. I'm going to swing down the negative 1/2, leave the inside alone, drop the power to a negative 3/2, times the derivative of the inside, which is 3x squared. So then all I did was combine this 3x squared and this actually is now negative, and this is negative. Sorry for those little edits. All right, so again, the one marked with the yellow check marks, that's what your final answer can be. But we should be wanting to clean them up and use our algebra skills, and in this case, our greatest common factor. Look that over, make sure you know how to do that. It's good.